Oh, are we ready to go?
Yeah, that's clear. Yeah.
Oh, okay, well, we're going to immediately go to the next slide. Just to remind you that I'm not so much interested in the heat transfer coefficient itself. What I'm interested in is finding ways to size heating systems based on the measured cooling and heating of existing buildings. So that's very much in the spirit of what David said earlier. So move on to the next slide, please. This really boils down to two questions. One is, if we measure the cooling of a building when the heating is switched off in practice, can we use that information to determine or to estimate the minimum temperature inside the room under design conditions? And secondly, if we know that temperature, can we use the heating response of the building to determine how much power, how much heat we need to put into the space in order to reach the set point at a particular time? So that's the essence of it. Next slide, please. We move on. That's it. Okay, so I'm going to show you some examples of analysis from data collected by Grant and Hitchin and his colleagues in Salford in their test houses, which, just to remind you, are well-insulated houses built within a space of where you can control the temperature, the outside temperature. I'll be focusing on one of their houses, which has been monitored with both continuous and intermittent heating at outdoor temperatures of +5 and -5, with a variety of heating systems. And I'm only going to pick up one particular subset of that because we haven't got much time and I haven't got all the data anyway. Move on then, please. So the example I'm looking at is heated by a heat pump and radiator system. Although it appears to have been designed according to the usual design practice, in fact, it wasn't able to maintain the set point or to reach the set point under intermittent heating. That's useful for me because it gives us a nice long extended warm-up period, which is long enough to actually try and see what's happening. Whereas in reality, of course, we're really only interested in warm-up over maybe 1 or 2 hours. Most of the data I've show you is fairly coarse. It's hourly measurements scaled from printed graphs. I do now have some more detailed data, which I'll show you one slide about. Yeah. So there will be more to come later, hopefully. So let's move on. Right. So the question is, basic question here is, how similar are the shapes of the curves under different circumstances? And we would like there to be an easy way of converting from one set of conditions to another. It would be nice if it was a linear process, which it might well be, thinking about the physics, but that remains to be seen. So let's move on to the first of the slides, for the first of the graphs, please. Okay, so what I've done here is I've taken the temperatures within the room. All the temperatures are from the living room, I might say. At fixed periods after switch off for cooling, which is what this shows, and regress them against each other for the two temperatures, +5 and -5. And you'll see that there is indeed good regression. There's an R² of 0.98, which is good. I'm not entirely convinced that the residuals are random, but that remains to be seen. What's interesting here is that the actual degree of cooling doesn't differ that much between the temperatures. In other words, from the start of cooling to the end of the cooling period, the temperature differences is not very different. What is different is that all the temperatures are consistently lower for -5 than +5. If we go on to the next slide, please. This shows what happens if you adjust the temperatures relevant or relative to the 24-hour mean internal temperature in that room. So in other words, just saying, okay, well, we know the 24-hour mean temperature, let's adjust them all so those are the same, and what does the variation look like? And that's what it looks like. which sort of leads to the idea that we're really looking at two processes here. One is a shift in the average temperature, which presumably reflects the outside temperature or the long-term outside temperature, maybe 3 or 4 days back. Doesn't seem to be, but and is definitely related to the outside temperature. And then an indoor variation of temperature, which seems to be only very weakly dependent on the outside temperature. Now, I have to say, these are houses which have low ventilation rates, so we're looking at a bit of a special case here, and they're well insulated. I think the other thing to say about this particular graph is that you'll see that there's a lag between or sometimes a lag between the two, the +5 and -5 measurements. That is not general. And when I've looked at the other situations, that doesn't usually happen. So that's something probably which is specific to this building and heating system, and we'll come back to that later on. So, okay, let's move on to the next slide, please. So that was the cooling down curve. We can do the same thing for the warm-up curve, and as I've said, fortunately we've got quite a long warm-up period, so we can have hourly measurements over about 5 hours. So it's comparable to the cooling curves. And here you've got an even better regression, 0.99 R squared. The temperatures, the offset of the temperatures isn't quite the same, but it's quite similar. And as you would expect, once you start injecting heat into the room, the rate of change of temperature is quite a lot higher. It's about I'm good on here, but I think it's about 2.5 times faster on the warm up than on the cool down. It's as you would expect, quite a lot quicker, but the same general shape, which is slightly surprising in my view. But there we are. Okay, let's move on to the next slide. So it raises the question, of course, well, are these actually the same curve, the same shape? And in fact, if you plot one against the other, you'll see that there is again a good correlation. So for periods of a similar time, you're getting very good correlation. As I've said, the warm-up time is much faster with the heating on. So if we can move on again. So this is one example I've got where I've used the detailed data and looked more closely at what's happening during the first 2 hours of warm-up. The blue line is the room temperature. The orange dots are the power from the heat pump. They're a bit scattered, but that I think is a function of the way they were monitored. Grant will be able to explain more of that to you if you need to know. But for the moment, just look at the general trends here, and I'll talk you through what's happening from left to right. So when the heating system when the heat pump is first energized, I should say to be accurate, for about half an hour, its power gradually increases. The temperature in the room doesn't change very much, and although I can't show them on this graph, I do have the flow and return temperatures to the radiators. I mean, I don't have them in a digital form, that's why I can't show them. So the flow and return temperatures don't change in that period. I don't really know what's happening here. It's not generic to all the tests by any means. I suspect the heat pump is either warming itself up to an operating temperature, or it might be going through a defrost cycle, which it's the first thing it encounters when it switches on. I really don't know. However, after about half an hour, it's running at full power. The room temperature starts to rise, which reflects the fact that the flow temperature has started to increase, and so has the return temperature. And for about an hour and a quarter, it keeps running at full load. And during that period, the flow temperature keeps rising. The return temperature keeps rising, though with a lag, and the difference between them increases. So what's happening in this period is that the heat is partially going into heating up the heating system, the water and the metal, various bits, but increasingly putting heat into the space. That's what the difference between flow and return temperatures tells you.
One minute, Roger.
Sorry?
1 minute. One
Okay,
minute.
I'm nearly there. So after this period, after this, the heat pump modulates down to a lower setting, which actually what it's doing is modulating down to keep the flow temperature constant. The heat input into the space is determined by the radiators now, and is not enough to raise the temperature to the set point. So I'll move on to my last slide. I resist the temptation to go into this in any more detail. If I go on to my last slide, please. Okay, so this slide's got a number of caveats at the top, but also it's got a list of questions which deserve looking at more closely, and my thoughts about how one could go about doing this. So you'll see that there are some things that more analysis of the test house data could probably help, particularly if I can get access to more of the detailed data. There's a question about how typical what I'm seeing is of other buildings and other situations. And I think simulation has quite a big role to play here of modeling a building and seeing how sensitive these characteristics are to variations of the building. But of course, really what we need to know to be sure is field data. And I'm less sure how useful, how easy it is to obtain that. The crosses at the bottom of this table, and it shouldn't be crosses, they should be question marks. That's a mistake on my part. So I'm rather hoping that some of the information that you're going to be gathering might be usable to take this further, with which I shall pass on to the next speaker.